from taking CS 315B. Okay. So I'm going to talk about machine learning. But before that, I wanted to get a sense of who here knows what machine learning is. You've heard of machine learning? What about you've trained a model before? What model? What have you trained?
A logistic classifier,
Okay.
linear regression, and a support vector machine and a neural network.
Well, that's pretty much everything. What have you trained?
Variable agents.
Okay. Cool. And then everyone else who hasn't trained a model, what kind of math background do you have? Just roughly. Probability? People study probability before? Cool. Okay. So machine learning is a lot of probability, understanding probability. It's also a lot of linear algebra. You have vectors with data, and you run them through models to understand your data set or what to do with it. And we're going to cover two main things today. One is this thing called linear regression, which is generally used to predict the future, as they call it in machine learning. Like you want to predict something that's going to happen, you might use linear regression for it. You might also use one of the other fancier models that he mentioned, but we won't really go into that much of the depth for those ones. Then the other thing you can do is this thing called clustering, where you have a data set, and you don't know what it's all about. But you know that you could group your data into 5 different groups based on some semantic meaning. And so you're going to run this clustering algorithm to automatically discover what the groups are. And then you can continue your discovery, look into the data, be like, oh, this group is about this group is about this. Kind of get more insight into what's going on. So I think I'm going to show you a bunch of code in Python that allows you to run these two algorithms. It's very simple in terms of the code, so I would suggest not getting caught up in the code and like what arguments you pass into the function and things like that, but focus more on the intuition for why you train a model in a certain way, what the data is, what could go wrong, things like that. And I'll ask you some questions along the way to verify that understanding. So it'll be nice for you to think about those as we go along. So the first thing that I wanted to run through, and a lot of this material was prepared by one of our other colleagues, Ashwin, and he couldn't be here, so I'm substituting for him today to help present this material. But I also do research in machine learning, so I'll give you correct information. I won't give you the wrong stuff. Okay, so here's a graph of a lot of dots. It's a lot of circles. You could draw this on a piece of paper. And it's nothing really fancy. But assume that this is a data set that you have. I just made this data set up in Python. Basically, I just told it, like, give me a bunch of dots with random positions on a Cartesian plane. Just give me x, y, random ones. What I want to do here is draw a line through these that captures roughly the relationship between all these points. And you could do that. How would you draw a line through this? Like manually, what would you do? You maybe start here, and then? Right. You just keep going. Oh, it looks like it's going in that direction. I'm just going to draw a line. And then that's your line. That's your line that kind of captures what this data is all about. You wouldn't draw a line like that, because then that's like all that data inverse, which doesn't make sense. So what we want to do is automate that process of drawing this line. Because once we have that line, it's powerful. We can do stuff with it. We can predict another point on that line, which is way up there maybe. Or we can compute all these fancy things like how far away a point is from that line versus another point that's away from that line. We can do analysis on the data that we have. So if you were drawing it manually, you might come up with 4 different people might come up with 4 different lines because there's like no way to be sure. But what we want to do is come up with the best line possible. And the best line in linear regression is defined by the line which is the perfect fit in the sense that all the other points are as close as possible to the line. So you may draw a line that's like really close to this point, but then maybe you'll end up being really far away from like a bunch of other points, and that defeats the purpose. You want a line that's as close as possible to as many points as possible. And that's linear regression. The other thing I mentioned was clustering. And here's the intuition for that as well. You have a bunch of data, and it somehow neatly falls into 5 groups. With your naked eye, you can see there are 5 groups. But the computer doesn't know that. Now, it would be useful to tell the computer or have the computer figure out that there is 5 groups. Because again, you can do some fancy stuff with it if it knows what the 5 groups are. You can do stuff like, if I have a new point, which of these 5 groups does it belong to? So this could be like if you're a company, you have users, 5 different types of users, maybe different age groups. When a new user comes in, based on their buying pattern, can you predict their age, which group they fall into? But that's only possible if your computer knows what the groups are. Does that make sense? And so you might want your computer to learn something like this. That's one group. That's another one. That's another one. And maybe this is like one group of its own. This could also be 2 separate groups. Depends on what you want your computer to learn, what you want the algorithm to like learn. Okay, now a little bit on the code side. As I said, don't like go gung-ho on the, oh, how do I call this function and things like that. We'll give you this later so you can like dive into the details. But scikit is this library that is very mature in Python. You can use it to implement almost any of the fancy algorithms that he just mentioned. And it's been around for a while. Everyone uses it. And there's only really 4 steps you need to do to implement clustering and or linear regression. One is you import scikit in Python. Very simple. The second thing is there are pre-built models in scikit that allow you to create a linear regression thing or a clustering thing. You instantiate one of those. You feed in some initial arguments. And I'll go over what those initial arguments are later. Then you give it some training data, and you call this method called .fit, which is the whole magic thing that happens where it takes the data and it learns that line, or it takes the data and it learns the groups. It kind of just does it for you. And there's a lot of intuition behind it, which is what I will talk about in a bit. And once you have that, you can then predict. That's the 4th step. So you import the package, you instantiate the model, which is already there. You give it some initial arguments. Then you give it the data that you have, and then you predict. And to predict, you need to give it a new data point. Then it will spit out some information, which you can then use to do stuff. Yeah, what's up?
Does scikit learn automatically dispatch to multiple processes, like through parallelization, or is it just single?
I'm not entirely sure about that.
Because usually I run this thing called the multi-process toolkit.
Uh-huh.
I think otherwise Python's single thread, but I'm wondering what it is.
Yeah, I'm not does Karthik know about this?
No, I'm not aware.
I don't know. Yeah, I'm not sure about scikit using that. But maybe I can read up on it later, let you know. Okay, so we'll first do clustering. And actually, wait, before we do that, does anyone have any initial questions on how the computer figures out this clustering thing? Do you like have any intuitions for how the computer might do that? How your algorithm might do that? It's this thing called the k-means algorithm. Have people heard of this? Okay, so those people who haven't heard of it, what do you think clustering is all about? Like, what does it mean to discover these groups from the data? How do you think you do it? I mean, I know you look at it, and then you're like, oh, there's 5 groups. But what if it wasn't that obvious? Yeah.
If the distance between any 2 points grows to be too large, then you create a whole new cluster for that extra point that isn't close to the other point that you've chosen. So you find the distance between all the points and then cluster it from there.
Correct. Did everyone hear that? It's this whole idea of trying to minimize the distance between points as much as possible. And if 2 points happen to be far apart, you put them into different clusters. And the threshold at which you have the perfect closeness of points and the distance of points such that they're in a different cluster altogether, like the threshold at which you get that nice balance is where you can say, all right, I have my groups. This is kind of like, and your eyes just do this automatically when you look at a picture like that. But the machine needs to be taught how to do this. OK, so this is a thing called the k-means algorithm. And k-means basically works through this. Here are the steps. When you have a data set, when you have this data set, for example, here's a new set of data with like groups that I just generated in Python. There's this thing called make blobs in scikit, the library that I just mentioned, where you can just create data like this. What I told it was I want 200 data points with 6 centers. So like roughly I want 6 groups. And then a group is the same as a cluster. Within each cluster, I want a standard deviation of 0.6. And that's like the distance, how compact the group is. And yeah, those things are not important. And then I just made a scatter plot out of that data. And then here you have your data set. So the algorithm is simple. You want to group this perfectly, right? You start out with picking n number of points, depending on how many groups you want. Let's say you want 6 groups here. You would take 6 random points, and you assume that those are the centers of each of your 6 clusters. Then you take all the other points, and you see, like you take all the other points one by one. For each one, you see, for the 6 clusters, the centers of the 6 clusters that you had picked, which one is it the closest to? And the one that you find that's the closest, you put it into that cluster. So then you just do that for every other point. At the end of this step, you have 6 clusters with points in them. Does this make sense, or did I confuse you? OK, cool. So then you have your 6 clusters. Yeah.
You said you go and look at each point, and if it's closest to it, you put that next in line, and the closest to it next in line. But you do that for all the points.
Yeah.
How do you arrive at 6 different clusters?
So you initially had picked 6 points out of these randomly, and you had designated them as your so-called clusters, as like the leaders of the clusters. Then you go through every other point, and for each of them, you compare it to those 6 points that you had picked. And if you find that the 5th one is what it's closest to, you put it in the 5th cluster. And then you just keep doing it for every other point. At the end of the day, you'll have, or at the end of that step, you'll have 6 clusters with a lot of points in them. Now, one cluster may have 0 points. One cluster may have a lot of points. That's exactly what we want to fix going forward. So then you have this initial set of clusters, right? Now, you know that initially those 6 points that you had picked were randomly. You just like randomly picked them. So they're obviously not the best leaders, the leaders to be chosen. So now what you do is you take those 6 clusters that you had created, you ended up with points, and you take the mean of all the points in each cluster. And that mean is now the new leader of that cluster. OK? And Now you have new leaders. You still have 6 clusters, but you have new leaders for each cluster. And then you do the step where you go through every other point and you compare it to these 6 leaders, see which one is closest to. You do that again. Does that make sense? Did I lose anyone? Okay. So then you can see what's happening. You see that there's a second round of re-electing the leaders by computing the mean of a cluster and assigning all the other points which are not the leaders. All the other points to those new clusters with new leaders. And then again, you would choose new leaders based on the new clusters that ended up being. And again, you would assign new points. And the idea is that if you do this a few times over multiple iterations, at some point, you'll achieve the most compact possible grouping. And that's where this algorithm will stop. And then you have your groups. What it will tell you at the end of that is, hey, I managed to figure out the groups here. I have all these points. Each point relates to some label, some group. And it'll just give the groups a label, like group 0, group 1, group 2, group 3. It'll tell you what point belongs to what group. And then you have your groups. You can visualize them after that. So
Is it guaranteed to reach a fixed point?
no. So he's asking if it's always guaranteed to find the optimal grouping. It's not. Does anyone know why?
It's an NP hard problem.
Yes, it is. It's what's called an NP hard problem, which is something that you can Wikipedia if you want. But there is a more intuitive answer for this. Yeah.
Groups may not exist. There might not be groups.
Oh yeah, yeah. I mean, sure. You may just have one huge blob, and if you try to like split that huge blob into 5 different clusters, then there is no obvious way that there are 5 clusters there. So there could be 1,000 different ways you have 5 clusters. Yes, but there's also one other reason.
Depending on the starting point,
Yeah.
they might cluster differently depending how you choose your initial.
Right. Those 6 initial random points that you chose in this case could be some weird edge case that could lead you to not a globally optimal selection of clusters, but like you could like get stuck at some point and not reach the actual nicely laid out 6 groups that you can see with your eyes. Okay. So the leader thing that I mentioned for each cluster is called a centroid. That's just the mathematical name for it. And we're going to quickly implement this where I take k-means and I import this k-means thing from scikit. I instantiate the model. And I say that I want 3 clusters. I don't want 6 clusters, I want 3. My initialization is random, which is what I just said. You like pick your leaders randomly. Then I want to run that update, that whole iteration thing that I mentioned. I want to run that 300 times. I want to choose my leaders 300 times, one after the other. The tolerance here is how close do I want the points to be within each cluster. And this is like 1 times 10 to the power -4 in terms of like distance, Euclidean distance, because we're talking about a 2-dimensional space here. Yeah.
Is n init the number of times that it runs the whole algorithm or something? What's n init?
N init is the what k-means does is that the whole process that I laid out just now of choosing the leaders and then like doing it 300 times in this case, it does that whole thing 10 times.
So it picks the random initial points.
10 times.
To make sure you get
Yes.
sort of like a convergence.
So that you don't get that weird edge case that I just talked about.
Gotcha.
then it kind of like, I think it gives you the best one out of the 10 or something like that. Or maybe it averages.
Most probable or something?
Yeah, I don't know exactly like what, but yeah. Probably the best one, like the most, the one with the least, the one with the most compactness in its clusters. And then this thing is not really important. Okay. Then that's my model. Now what's the next step? Once you have your model, what do you do? Predict, really? Your model is, a model doesn't really know what your data is.
Train it.
Yeah, you train it. You give it your data, right? For k-means, there's this thing called, here, there's this thing called fit predict, which is like a combination of training and predicting. Because in k-means or in the clustering thing, you kind of know what you want to predict. What you want to predict is you have this group of data, and you want to split it into groups. So at the end of the day, what you really care about is what cluster does each point go to. And that's your prediction. So when you call fit predict on your data set, it will group it and then spit out what cluster each point belongs to. And that's where your y underscore km variable, that's what it's going to hold. So we can print that quickly. All right, what do you think this thing is? What's this? It's like an array of numbers, right? What is that? Wait, someone who hasn't said something? Yeah.
It's the groups that it's predicted each point to be in.
Right. It's basically group 0, group 1, group 2. And we said we want 3 clusters. So that's group 0, group 1, group 2, 3. And these are all the points, basically. Like, I don't know what point this is, maybe like the 20-something point goes to group 0. All of these go to group 0. Then, like, I don't know what this is. Maybe the 50th point goes to group 1, 51st point goes to group 1, and so on. And then I want to visualize this because it's kind of hard to see what's going on in this array. You don't know like what's what. So I just have this code here to put a scatter plot out of this. And then here I see my data, which has colors in it. You can't see the white. There's this white group over here. I don't know where is that. Yeah. Yeah, machine learning people don't really have a good sense of art or like what looks good. We just like train models, that's it. But you see the groups here, and you see it's done a pretty decent job at discovering that like maybe this is a group, and then like that's a group, and then everything else is white. And then these are the centers that it found, the leaders. At the end of the 300 iterations, leader, leader, leader. Yeah?
Does the centroid have to be a real point?
No, great question. The centroid doesn't have to be a real point, and it probably won't be a real point.
That doesn't look like a real point.
Yep.
Too young.
Yeah, it's not a real point. Do you know why? How did you come up with the leader? Okay, initially you chose it randomly. So it was one of the points. But after that, on every iteration, you've been choosing leaders how? What? By taking the mean of all the points in the cluster. Now the mean is not guaranteed to be one of the points. It could just be some other random point, right? You may not have that mean in your data set, but it's the mean, and hence you let it be. Okay. See how much time I have. Okay. Let's go to linear regression. Okay. So again, for regression, I have what I had before, the whole idea of a bunch of points, and I want to draw a line through it. So what I'm going to do is to instantiate a model. Again, it's simple in the sense that there is this linear regression thing in scikit. I'm just going to instantiate it, and there I have my model. I'm going to take my data, which is this thing that's in right here, X. This array that holds my information. And we can print X to see what it looks like. Yeah. Da, 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 da. And then we can also print Y to see what it looks like. Okay. So it looks very complicated, but it's just like a bunch of x's relating to their corresponding y's, where the y was, where this y corresponds to this x, and then the y was obtained by using that equation over there, y equals 2x plus some intercept. It's just like a linear equation, because that's kind of what we want. So okay, what this tells you is that there is a relationship between the x's and the y's. And the relationship is that equation over there, because that's how we came up with the data. So the goal of linear regression here is I'm not going to tell the model what that equation was, but I'm going to give it this data. And I hope that by analyzing the relationships between the x's and the y's, it's going to figure out that that's the equation. That's a linear equation that actually relates the x's and the y's. Does that make sense? So you hope that it's going to discover on its own the y equals 2x plus EPS, where EPS was some random thing. And that's the powerful thing about this. Actually, yeah, why do you think we might want to do something like this ever? Who cares, right? Does anyone have an intuition again for why we might do something like this?
Why give it a node?
No, like why would you ever want to like learn this equation behind the data? Like what? Who cares?
To know the deviation in the errors like from our ideal scenario was expected.
Sorry, say that again?
To know how much we are deviating from our ideal scenario in general over the whole process.
To know how much we're deviating from the ideal scenario that we thought was the case.
Well, you know what
Okay,
the equation is, you can
maybe.
model it at a later time.
Sorry?
You know what the model or the equation is, you can use it for later.
True, yeah. If you know the underlying relationship between your x and your y, then you can use it to create more x's and y's that fit that relationship. What else? Actually, were you saying something? Okay. Yeah.
We can just use it for general prediction.
Okay. Like how?
So since x is just it's just a regular array of incremental points. If you know the relationship between x and y, you can just extend the x's infinitely into the future, and then you can figure out the y's associated with those x's.
Yeah. Yeah. So like if you have a stock price in like, I don't know, Snapchat, right? They had an upward thing very recently, IPO, upward thing. If you use that data, and maybe this is your Snapchat data, where the y is the stock price, and then your axis is time, then you can learn a model to be like, oh, this is how with time Snapchat's price tends to go up. And then you may run into a problem, which is, what's wrong with learning this equation and then being like, I know what the data is all about.
The equation changes with time.
Yeah, the equation could change. Like Snapchat now is going down. They're kind of getting destroyed. And so the stock price is going down. So that equation will no longer reflect future data. And that may very well happen. That's why when you generally build models like that in industry or whatever, you'd tend to update your model continually with new data. You keep improving it. You keep adjusting your understanding of what the data is all about. And if you don't do that, then you'll predict that Snapchat stock is going to go more, it's going to keep going higher and higher, and then you go buy it, and then you'd lose money. So it's important to understand the relationship between the data so that you can make better decisions about buying shares, like anything that you can imagine. So once we have that, okay, let's do the same thing as we did before. Yeah.
Earlier, initially, we have been given only with the data set, right?
Mm-hmm.
So why did we start thinking in terms like maybe we should find a linear fit? Why not why did we not think like there might be some quadratic fit or some cubic fit
Right.
that suits the data better
Yeah.
for future prediction? Like
Yeah.
why only linear?
So why did we only try and fit a linear model, like a linear equation? Why do we think that a linear equation is the best way to go? Any ideas? Yeah.
Because in this case, that's how we told it to generate the plot using a
Okay.
linear
So you already know what the data, it came from a linear equation. So hence you should model it using a linear equation. What if you didn't know that?
then
Actually, wait, let's say I have someone else. Hamid, do you want to? Why did we go with a linear equation for our model?
Is that the simplest case?
Okay, yeah. It's the simplest thing, right? There is nothing lesser than a linear model. A linear model has one variable, x. Y equals something x. So it's the simplest thing you can start with. It may not be the best, but then you could go to quadratic right after you do linear. So yeah. And then there's also a third reason. I'm looking for people who are making eye contact. Most people are not. Avoid overfitting, yeah. No, that's the fourth reason actually. Overfitting is relevant to your final project, so you should know this. Who knows what overfitting is? Have you heard of put up your hand straight. Who has heard of overfitting? Who has not heard of overfitting? Like, doesn't know what, it's not like a clothes fit or anything like that. Okay, so what if you tried to draw a square, so his question was, why not use a quadratic formula? What does a quadratic formula look like? Like that, right? Or maybe like this. So to this data, what if you tried to fit a quadratic equation onto it? You might, you might get something like, I don't know, like ta-da, like something like this maybe, or maybe something like that, or some weird thing like this. You could get a bunch of different things that don't really capture what the data is all about. Like you wouldn't want your model to be like that, right? Because yeah, it is following the data in the sense that there's a few points here, so it's following that. Then it's following this big cluster here, so it's going down here. And then it's again using this cluster to like go up. But it kind of overfits to the data. It's like too specific to this data. And the problem with this kind of a thing is that your model is too specific to the training data, to this data. Does that make sense? Why is a model that's too specific to the data, why is that bad? You were nodding your head. Why do you think it's bad?
You're asking?
Yeah.
Well, I mean, the data could definitely change based on how you collect it and things like this.
Yeah. your new data that you want to like predict on could be different. And then your model won't know what to do. It's like, okay, this is an example that I have personal experience with. If you're in college and you get very used to taking classes really, really well, and you can like game your way through all the classes, and you know how to get those A grades because you go to office hours, then you go into industry and there's no one there to help you, then you suffer because you're like, oh man, like I need office hours. But like there is no office hours in when you go out and work. So you've kind of gotten too used to that one way of working, and then you need to adapt. So it's kind of like you just overfit yourself. Your working style was like overfit. I mean, yeah, it kind of makes sense, right? You kind of overfit to the working style in college. So it's kind of something like that, just to give you the intuition behind it. And so that's why our earlier point was, that's why we start with a linear model. Here it's okay. Even in other circumstances, you would start with a linear model and then gradually maybe go to a quadratic or something, or a cubic. So then we have our model. Then you fit it. Same thing as before. Create the model, give it the data. Giving it the data is fitting. Where here you're saying, here's my x, here's my y, go learn the relationship. Go figure out that linear equation that relates them. And then I can use it to predict stuff. I can say this thing, this line over here. I can say, here's my new data that I want you to predict y values for. So I'm going to give you new x's. So in the case of the Snapchat, if this was like Snapchat stock price, I'm going to give you new points in time. Tell me what Snapchat's stock price would have been. Maybe the new point in time was in the past or the future. And so YPred consists of all those predictions. And then I'm just going to plot it. So this is the line that we got. This is the line that our model learned through the data. It could have been like that. It could also have been like this, but those wouldn't be optimal based on the math. So it chose to do this, and then this is the best one. And we can also tell it to give us what that linear equation was that makes that line over there. And you can just print it out, model.coefficient. Coefficient is the y equals ax plus b, then a. A is the coefficient, and then plus b. B is the intercept. Okay, and so that's basically linear regression. I wanted to also talk about how you evaluate these models. Yeah.
In the model that's predicted, it seems to add a random variable for noise.
Mm-hmm.
But the coef is not telling us the variance of, let's say, the Gaussian random variable. Is there a way to pull that out?
I'm sure there's a way, but I'm not, right now, sure. It does tell you what value it think it should be, the noise. The intercept? You mean the intercept?
Yeah, it seemed like if I were to predict this model, I would have given it just a straight line instead of adding additional noise onto it. So I'm not sure what's the variance.
No, so there isn't really additional noise here. There is an intercept. All there is a y equals ax plus b. And it's trying to learn the best A and B.
That's right. But when you run the predict function, right, it's not giving you just a straight line. It's giving you deviations from the straight line. Like it's not y equals ax plus b, it's y equals ax plus b plus n, where n is the I and event.
Yeah. Yeah, what about that?
So I feel like what's going on is that it's not just predicting with y equals ax plus b, but there's some additional noise on it. Otherwise, it would just be a straight line.
It will be a straight line. It is, all it's doing is you're giving it a new data point, which is the x, and it's going to pass it through that the y equals ax plus b.
So that blue line is the y equals ax plus b. Okay.
The blue line is the y is equal to ax plus b.
Okay, thank you.
Yeah. So you could give it a new x and kind of just like, oh, x, great, that's the y. Just read it off. Okay. Yeah, I want to talk about how to evaluate these models. Who's heard of ideas like precision and recall? Precision. Haven't heard of precision. What the hell is precision? Recall? What the hell is recall? Okay. This is something that you'll see in your final project as well. And so it'll be useful to have an understanding of what that is. Now, when your model learns a function for your data, you're then using it to predict something, right? And chances are that prediction that you're making is wrong. And how do you know it's wrong? It's because when you go through this process generally, what you do is that you train your model on some amount of data where you give it the x and the y. And then you reserve a small amount of data that's called the test set. The test set is data that you have the y values for. You have the real y values. You don't really need your model to help you predict what the y values are. But what you use that test set for is to see how good your model is. You'll train it on the training set, which is a bunch of x's and y's. And then you're like, OK, well, my model knows a little bit about the x's and the y's. Here's a test set. I will tell my model to predict on these new x's that it has not seen before. So in this case, it could be I have given it all these points to learn from. But now I'm going to give it another 50 points, where those 50 points are further down the timeline. There's like somewhere here. And I'm going to tell the model, give me the y's for these. Go predict the y's for these. And then it gives me its predictions. And I compare those predictions to the actual y values for those new points, because I know the actual y values for those new points. And the model is going to give me its prediction of what it thinks the y values should be based on that equation that it had learned, that line over there. So now I can compare it, and I can judge the model and figure out how good it is. Does it match the actual y values, or does it not? And then here's where there's this two really important thing. Like if you go to a machine learning interview, they're going to ask you, what is precision, what's recall? And if you talk to people about any of this, they'll be like, what's the precision, what's the recall? Precision is the idea that if my model, out of those 50 points that I mentioned, the new 50 points that I told it to predict on, if my model says that 20 of those were of class 0, of y value 0, but in actuality, there are, no, I'm flipping this. Let's do recall first. If in your 50 points, the new 50 points, if 20 of them have actual y value 0, okay? Your model is asked to predict what the y value is on those 20 points. And your model says that 18 of them have y value 0, predicted y value 0. It says that 2 of them are some other y value, maybe 1 or 2. Then what you have here is 18 divided by 20 is what it managed to get correctly. It should ideally have said, yeah, all these 20 points are class 0. But instead, what it said was 18 of them are 0. And this, yeah.
So it's never gonna, you're never going to actually predict 0, right?
It is.
No, because well, that's a model, right? You're never actually going to predict the exact number to 6, 18 decimal places. So is there a standard like this percent away from?
No. So generally, when we talk about these measures, you like assume it's kind of like discrete. So it's kind of better suited to the clustering example, where there were distinct group 0, group 1, group 2. Yeah, it's in this group or it's in that group.
So linear regression is more predicting whether it's in the correct group.
Yeah, so in linear regression, the way that you'd apply this concept is you'd, instead of, you could have like a measure of like how close is your y value to the actual y value that you know of. And then you can do something like what's called the root mean square error, where you take the difference, you square it, and you sum it up across all your y's. And then you get this like value that represents how close you are to the actual y values.
So then to quantify the recall, you say it's within a certain range from the model, you assume it did predict.
Yes.
Is there a standard on what that value is?
A standard on how you do that.
Like are you normalizing by the model and then you say, oh,
Yeah.
X%, it's okay.
Yeah, I don't know if there's a standard. It really depends on the domain and the data set that you have. And so it's a lot of looking at the data and trying to see how much am I comfortable with. But in the clustering case, it's pretty obvious. And so, again, recall is the idea of out of those 50 points, 20 of them are actually y value 0, group 0. Your model came along, and it predicted a bunch of those points to be in group 0. But out of those that it predicted to be group 0, 18 of them were group 0 in its predictions, whereas actually there are 20. So the model managed to recall only 18 of the 20. Does that make sense? It's kind of like it should ideally have gotten all 20, but it only managed to recall 18 of them. And that's why you call that recall. And then precision is how correct was it when it predicted a bunch of points to be group 0. When it said that out of these 50, 18 of them are group 0, maybe not all 18 were group 0. Maybe only 10 of them were group 0. So it was wrong partially. And the precision that it managed to attain over there was 10 divided by 18. The idea that when I say something, how likely am I to be correct? This will be one of the output values in your final project, which is due on Saturday. And then you're supposed to like submit this to us with an essay on what this means. No, that's not true. But you should understand what these two things mean and come to office hours so that you understand this. Like that's the whole point of this lecture, to understand these two models and like know what this precision recall thing is. And then I also wanted to finally talk about the deliverables quickly for the final project. A few people had questions in office hours. You're basically supposed to submit to us the confusion matrix that will be the output of your model. And you're supposed to give us a table with the precision and the recall and 2 other measures of your model. The model that you're going to implement is what's called a neural net, and it's like kind of very famous nowadays. The interesting thing about a neural net is kind of relates to your question about why don't we start with a quadratic function or whatever. A neural net is pretty fancy in that it can learn any function. It can learn a linear function. It can learn a quadratic function. It can learn a 1,000-dimensional function where there's like something to the 1,000. It can learn a bunch of different functions because there's a lot of parameters to it. And that's why it's all the rage right now, because it's like speech recognition, all the driverless cars, they use a lot of neural net stuff because there's like very, very powerful. You won't use linear regression in that case. But there's still, in 99% of use cases, you would still use things like this. Like you go to any company out there, they would generally have a data science team where they're looking at how their users use their websites, tracking what they click on after this and this. And then at some point, they want to predict what the user is going to click on. Boom, they'll use something like this. Because they have data about what the user is doing. Now they just need to know what the user is going to do next. And maybe they'll be wrong, but they can try. Amazon, they can try and price their products based on what they think the user is going to do. They'll use something like this. And the good thing is that when you submit those deliverables, we have functions ready-made for you. Scikit creates the confusion matrix for you. And it also creates the precision recall table for you. So you might get away with not understanding anything, and that's fine. But I do think you should try and make sure you really nail this. I'm going to be around here after the lecture if you want to talk more about precision recall. And then office hours on Saturday, 12 to 1. Same place, at the CTR room. And then we have 8 minutes. So I want to see if you have any questions. Yeah.
You don't have to submit the source code?
You do not, I believe, no. Because it's like a Jupyter